limits and continuity questions go. Pretty good. Any quick questions on those?
Yeah, just so I know I did it right, can we go over this one?
That's why I send you the answers so you know if you did them right. That one?
Yes.
So, we're talking about a limit as x approaches infinity. We can say that 4 plus 1 is approximately equal to this. Right? It's not actually equal to that, but if we're talking about as we approach infinity, it is about equal to that. So, if I plug in infinity, we get infinity over infinity, so we can think about L'Hopital's rule. So I can say this is the same as the limit as x approaches infinity of 6x over 8x. I get infinity over infinity again, so the next derivative, and we would just get 6 over 8, which reduces to 3/4. Any other ones real quick? Alright, this was, I think I went through like 3.5 tests, previous tests to get these questions, and there were what, like 20 questions? So that breaks down to maybe 6, 7 of these questions on the AP test. Okay, so I mean you're gonna see questions like this. Okay. Today then we are going to do our derivatives review.
Ooh, I'm not sure.
Apparently I forgot to make this 2-sided when I printed it out, so 4 pages instead of 2.
Why are you looking at me like you want to kill me? Okay. Stab their eyeballs out.
Yeah, don't do that.
I mean, she said she wanted to kill everyone, so.
The copier seems to be randomly choosing pages that 3-hole punch instead of 3-hole punching all of them. I don't know why.
Because it wants to sass you.
Maybe.
How can you have 2 of them?
Yeah, I have 2 of them hole punch.
I only have 1.
I think it was like, well, these were supposed to be 2 papers. So I'm only going to hole punch every other one because they were supposed to be 2 papers.
Maybe.
Alright. Today is just a review over differentiability, average and instantaneous rate of change, a whole bunch of derivative rules. Alright? So first, differentiability. A function is not, that shouldn't say continuous, that should say is not differentiable. A function is not differentiable at a corner, cusp, vertical tangent, or discontinuity. Right? So the most common way that this idea shows up on the AP test is in a piecewise function. So this is a nice example. It says if f is the function defined above, then f prime of -1 is what? So we want the slope at -1. Right? Well, that's where this function breaks. Okay? It is possible for the derivative to exist there if the slope at each of these pieces is the same. So what I would want to do is just take the derivative of each piece. So we would say f prime of x equals, the derivative here would just be 3, right? And this one would be -2x. So if I plug -1 into each of these pieces, well, this would obviously just stay 3. And then -2 times -1 would be +2. So it doesn't exist, right? So the visual of what's happening here, so we're saying at x equals -1, the slope of the first one is 3, and then the slope of the second one is 2. So even though it's a slight change, technically that's a corner right there, okay? Since it's not a smooth transition between these slopes. And so something like this is probably the most common way that differentiability would show up on the AP test. Okay? And that can certainly also show up on graphs, right? We looked at a lot of examples of pre-response questions where we had to say, well, since we had a corner here and here, the function isn't differentiable, that kind of thing, right? The next idea we looked at was average versus instantaneous rate of change. Okay, average rate of change is just the slope between 2 points. Right? It's the slope of a secant line. Instantaneous rate of change then is the slope at a single point, the derivative. So here is a question that asks us to estimate the instantaneous rate of change using the average rate of change. So given a table, right, it says Ruth rode her bicycle on a straight trail. She recorded her velocity in miles per hour for selected values over the interval. And we want to use the data in the table to approximate Ruth's acceleration at 1.4 hours. So we know that acceleration is the derivative of velocity, right? So if I want to estimate the acceleration given points on a velocity curve, I would want to find the slope. Okay? So if I want to estimate the slope at 1.4, I want to find the slope between these 2 points here. Oh, I was stuck. I figured.
We'll just show that. Yeah, she knew that, actually. I met her. She was like, we're going to come get you. And then she did. And so then we just got up and left. And it was like really uncomfortable. We were out there in the front. And we passed her in the hallway. She's like, you couldn't handle it? And we were like, no, we have class. And she was like, oh, true. Like, yeah, oh, true. She maybe.
Alright, so all we're doing here is finding the slope. So V of 1.2 minus V of 1.6, so 17.2 minus 16.3 over 1.2 minus 1.6. So 1.1, or I'm sorry, 0.9 over negative 0.4. So we can just say that's negative 9 over 4, or negative 2.25. So if we are using acceleration, what would my units of measure be here? Miles per hour per hour. Okay, so that's an example of average rate of change. So that part A in a free response like that would probably be worth 2 points, right? And all we did was find the slope. Okay. Questions so far?
All right, then the next part is all of our derivative rules.
So I'll just make up some examples as we go through these. So the first few that we looked at were power rule, product rule, quotient rule. Okay, power rule is just if we have a polynomial, okay, some variable to some power, like 4x cubed, derivative, we bring the exponent down and multiply by the coefficient. So we would have 12x and then subtract 1 from the exponent. Product rule says that if I'm multiplying two functions together, like, let's say x times cosine of x. Right? Multiplying two things together, we would have to use product rule to find the derivative. So product rule says derivative of the first times the second. So derivative of x is just 1 times the second would be cosine plus the first times the derivative of the second. So derivative of cosine is negative sine. So this would just be cosine minus x times sine. We wanted to simplify that. Alright. Quotient rule says if I'm dividing two functions, I have to use this rule. So, I don't know, how about x over, let's make it easy. How about just x over x plus 7? Something like that. So the derivative here, use my quotient rule, says square the bottom. That's the first thing we did. So x plus 7 squared, bring the denominator straight up, times the derivative of the numerator, minus the derivative of the denominator, in this case would also be 1, times the numerator. Okay? These rules just have to be memorized. Okay? Good with those?
Alright, then chain rule.
We have a function of a function. To take its derivative, we have to think about layers. So if we get h of x equals about sine cubed of 4x squared. So this one actually has a couple of layers, right? Now, whenever we did trig functions, remember we talked about rewriting them with the exponent on the outside, okay? Because to visualize the layers, I think it makes more sense to move that exponent. Trig functions look tricky because we put that exponent kind of in the middle, which is weird. So to look at the layers here, the outermost layer is the cube. So to take my derivative, all I worry about is that layer first. The inside does not change, so I will still have 4x squared on the inside. Let's subtract 1 from the exponent. The next layer then is the sine function. So I take the derivative of the sine function and don't change the inside. And my next layer is the 4x squared. So now I would multiply by the derivative of 4x squared. So this one had 3 layers to worry about. Okay, so we just have to look at layer by layer and take the derivative of the outermost layer, not change what's on the inside. Okay. Good with that? So then we've got all of these rules. Our trig derivatives, our inverse trig derivatives, and logs and exponentials. So these, just have to be memorized. Trig functions, I can pretty much guarantee you will see some of those on there. The inverse trig functions are more rare. Okay? Those do not show up very often, but they do every once in a while. If you want to not memorize these, you're probably only going to lose a point or two, right, on the AP test. These ones are much more important than these. So if you think you only have so much mental capacity to memorize things, I guess this section would be what you would leave out. Right? So, I mean, obviously these can show up in any product rule, quotient rule, power rule, chain rule. Ones that we haven't really looked at yet are logs and exponentials. These are also pretty common on the AP test. So I gave a couple of simple examples here. If we have an original function 4 to the 3x minus 7 power, then the derivative is the exponential. So I just rewrite the exponential times the derivative of the exponent. So the derivative of 3x minus 7 is 3 times the natural log of the base, and the base is 4. Commonly, they will have exponentials with a base of e. Right? That they like to have exponentials with a base of e and logs with a base of e, because what happens is when we take the natural log of e, that's just 1. And so, for example, if we had some function e to the sine of x, say, well, its derivative then would be e to the sine of x times the derivative of sine, so times cosine, times the natural log of e, which is just 1. So we don't need to write that part. Similarly with logs, if we have a natural log, say natural log of x squared plus 7, well, the derivative is just the derivative of the inside. So that would be 2x over the inside times the natural log of the base. The base of a natural log is e. So times the natural log of e would just be multiplying by 1. Questions on those? All right. Then another topic that I can pretty much guarantee you will show up in some way is a tangent line. Writing the equation of a tangent line. We need two things: the point on the original curve and the slope at that point. And so, as an example, I want to find the equation of the tangent line and the normal line for this curve at x equals 2. So the first thing I need is a point on the original curve. Well, to do that, I'm just going to plug my x value into the original function. That'll get me the whole point. So what is that? 4, 8, minus 6 is 2, plus 1 is 3. So my coordinate point is 2, 3. Now I need the slope at that point. To find the slope, I need the derivative. So f prime of x will just be 4x minus 3. So then plugging in 2 for x, f prime of 2 is 4 times 2 minus 3 would be 5. So now I have all the information I need. And I have that my slope is 5 at the point 3. I can write the equation of my tangent line now. So I'm using point slope. Okay. Y minus y1 equals m times x minus x1. So I just plug that information in there. So y minus 3 equals 5 times x minus 2. Now, it also asks us to write the equation of the normal line. What's that? Right. It's perpendicular. So all I'm going to do is take this information, but use the opposite reciprocal slope. So the point stays the same, and I'm still using the point 2, 3, but now my slope is negative 1 over 5. So the equation of the normal line would be y minus 3 equals negative 1/5 times x minus 2. And I guess I should label which one's which. And we'll look at implicit differentiation here in a second, but recently it seems like tangent lines of implicitly defined functions have become a popular question type on the AP test. Okay? But it's the same process. Right? You just need to find the coordinate point, you need to find the slope at that point. Okay? So, approximating using tangent lines is also a popular question type recently. Right, so this is just writing the equation of a tangent line one step further. Okay? It's saying, write the equation of the tangent line at this point, and then use that tangent line to approximate the actual value of the curve at some point close to where we wrote that tangent line. So here, okay, we're saying we want to write the equation of the line tangent to the graph at the point where x equals 1. And in this table, we're given values of the original function and of the derivative. So first, to write the equation of the tangent line, if I want to collect my two pieces of information, the point and the slope, okay, well, I want that x equals 1. So if I go to x equals 1, it tells me the y value is -4. So right off the bat, I know that my coordinate point is 1, -4. And then this table actually also gives me the slope that I need. And it also tells me that f prime of 1 is 5. So I can collect the information I need just from the table. I didn't have to do any work, find any derivatives or anything. So the equation of my tangent line here would be y minus -4, so y plus 4 equals 5 times x minus 1. Now the second part of this question says, use this line to approximate the value of f of 1.2. So all we need to do is plug 1.2 into this equation for x. So I'll have y plus 4 equals 5 times 1.2 minus 1. So, well, actually, let's just get in the habit of not even trying to simplify. Okay? All I need to do is subtract the 4 over. Right? For the AP test, we actually want to get in the habit of not doing arithmetic. Leave it like that.
That just sounds like a contradiction.
It does, but that is a perfectly acceptable final answer, and that leaves less room for error. Right? I mean, if you try to simplify this, you might mess it up somehow. Okay, so just don't do it. Just don't simplify it. Just leave it like that. If you have an all numerical answer, that is perfectly acceptable.
How do you know if it's greater or less than if you don't simplify it?
So to finish out this part, then we need to look at another piece of information that we're given. So what we're told is that second derivative is always positive, which is, we're actually, this is part of what we'll do tomorrow. We can talk about applications. But what does that mean?
Concave.
It's concave up. Okay? So if my function is concave up, okay, and I draw a tangent line at any point, okay, let's say right here. If I draw a tangent line here, and then I pick a point, say over here, does that over or underestimate the actual value?
Underestimate.
Right? So we would say that underestimates because function's concave up. Okay, you okay with that one? Yeah, right?
Yeah.
All right.
All the rooms are like different temperatures, and this room is always the coolest.
So I've got a cold heart. All right. Implicit differentiation. Basic idea here is just if we have a function that has x's and y's in it, whenever we differentiate a y, we have to tack on a dy dx. Okay? So let's take a look at this function and just find the first and the second derivative. Okay, so to find the first derivative, I'm differentiating just like I normally would, right? So I'm using power rule here. Bring the exponent down, subtract 1 from the exponent. But whenever I differentiate a y, I have to tack on a dy dx. Derivative of 2y cubed would just be 6y squared dy dx. I don't do that with the x's. So the derivative of x squared is just 2x. But then the derivative of 3y would be 3 dy dx. Next step is to get all the dy dx's on one side and everything else on the other. So I can just subtract this 3 dy dx over. Right, say this is now 6y squared dy dx minus 3 dy dx equals 2x. Right, the whole point of doing that is now I can factor a dy dx out of everything on this side. And now just divide both sides by 6y squared minus 3. So we end up with dy dx equals 2x over 6y squared minus 3. Now, how do I take the second derivative? How do I take the derivative of that? Quotient rule. Okay. So, it get messy real fast. So just nitpicky on the notation. Remember, if we're taking the second derivative, we write it as d squared y over dx squared. Right? So to use quotient rule now, first thing I do is square the denominator. So 6y squared minus 3 squared. Bring that denominator straight up. So 6y squared minus 3 times the derivative of the numerator. So the derivative of 2x is just 2 minus the derivative of the denominator. So that'll be 12y dy dx minus 0 times the numerator, so times 2x. Right, so the final step is we want our second derivative just in terms of x's and y's. So I want to replace dy dx with what I already know dy dx to be. So this will just become 6y squared minus 3 times 2 minus 12y times 2x over 6y squared minus 3 times 2x over 6y squared minus 3 squared.
Leave it.
Leave it be. You okay with implicit differentiation? Okay, now, like I mentioned, it has been a popular topic the last few years to ask you to write the equation of a tangent line of an implicitly defined function. Right? So it would be the same process. Right? We would just want to, and a lot of the time we're given the entire coordinate point vector. So then we would just plug our x and our y into the derivative to get the slope at that point. Use y minus y1 equals m times x minus x1. Questions? All right. We did pretty well today then. Got the rest of the time to work on the practice multiple choice questions that are attached.